Okay, welcome to the lab session, basically, where we'll be doing a little bit of lecture and also a lot of problems, hopefully. And we're not going to take the full period for it, but at least some time from it. And then the other thing we were talking before the recording started, actually, is for the Mars Rover Challenge. You should have received an email from the SAM Center. And I'm hoping as many of you participate and have fun, basically, with it. And enjoy yourselves, basically. Try to devote some afternoon for it, and hopefully you guys do the challenge and send it over. The 11th is when you're supposed to submit it, and actually the 12th when we're going to meet and basically discuss that and discuss future projects and things like that. And I was already whining about the fact that this corona prevented us from doing fun stuff, such as actually building an actual replica of a Mars rover on campus with the, of course, the physics and the engineering club. So that's the thing that I was hoping we do, because that's usually where I hang around in the STEM center with the people there and try to do things. Anyway, so I'm hoping that you guys who are not here right now and watching this recording later to also take advantage of this opportunity. So let me finish a little bit of the lecture. And then we're going to do problems. I actually added another problem to the mix because of its importance, okay? And that's problem 43. So I know we did problem 52. I know we did problem 53. I know I promised we will talk about problem 55. We'll try to do problem 55, and that is all data problem. And then we will, I added to them problem 43 to the mix. Problem 43 is actually a very nice problem. That is usually something that drives a lot of points in Word, okay, using Gauss's law, of course. And I don't know if I've been saying 61. What I meant with those problems that are similar to 52 are problem 62, actually, not 61. If I ever said 61, I was mistaken. 61 is a little bit of a hard problem. I did it last time. Basically, I solved it and put it on Canvas for those who are interested in it. It's not really that useful problem, honestly, but problem 62 is. Problem 62 and problem 47 are. Okay, so those two are not doing them because we already did problem 52. And I assume that if you do problem 52, you should be able to at least start those problems. Because both of these problems have the same element of volume dV equals to 4 pi r squared dr. And the integration over the charge in this case is the same thing, going from 0 to wherever you're supposed to go for r to find the charge. And the Gaussian surface, because of the fact that they all have the spherical symmetry, is going to be a sphere. So the area of a sphere is 4 pi r squared. The details and how rho changes with r, that's all. Because all of these three problems are non-uniform distribution of charge. So you should be able to handle those kind of problems, okay? Does this make sense, at least for these two problems, 47 and 62? In principle, I know that probably the details, when you start doing them, you will find some difficulty, which I really want you to experience. Is the principle clear? The method, I should say. Yes, no? Okay, and this is not a democracy, okay? You guys are supposed to vote one way or the other. You cannot say, I abstain. Is the method clear or it's not clear? One or the other. I need some feedback. Come on, guys. Okay, at least Milo agrees that it's... So basically, just to repeat, and again, please try to do them so that you understand the content. You cannot understand unless you do them. The charge is not uniform. So it's not equal to rho times the volume anymore, because rho changes with the volume. So you cannot pull it out of the integral. You have to leave it inside the integral and integrate. So you leave rho inside the integral and integrate. You cannot take it out. If it's uniform, you take it out and you're done. But it's non-uniform. the element of volume in this case is going to be, because of its a sphere, the element of volume is going to be 4 pi r squared dr. And you integrate from wherever you're supposed to go. If the entire volume, you go from 0 to big R. If it's from somewhere in between, you're going to go to 0 to R, and so on and so forth, okay, for all of these three problems. That is one part of the problem. The other part of the problem, you're trying to find the area of a sphere. The area of a sphere is going to be, because of spherical symmetry, is going to boil down to just multiplying E times the area of a sphere, and the area of a sphere is 4 pi R squared. So that knocks down this part of the method that we're using for this kind of problem. The other one, to make the calculation easy, we make the transformation of R over big R, the radius, the distance, I mean, the radial distance R, over the radius of the sphere as a unitless variable U, and that is a typical transformation that we use in these problems, okay? Then instead of dealing with R all over, and then probably we forget one and things like that, we pull it during the change of variable, and then we will end up with a number, like 12 or 27 or 223. It doesn't matter, a number with no dimensions in it. So that is the result of the integration at the end of the day. It turns out an easy number for our case for problem 52, where that number is exactly 0, okay? And we came up with an explanation for the answer, and we understood it and everything else. So this is the method in general. So if you're in doubt what to do next, when you're going through these problems, just go back to the problem 52, go back to the video if you didn't take notes. If you took notes while we're doing that, go back to your own notes and see where you stand in the approach of the problem. Are you in this level, at this point? Did you reach this stage? Are you at that stage? Which stage you are in the solution of the problem? Then you can pick it up from there in the particulars of those problems, okay? So that is basically how this is going to be handled from now on, at least this kind of problems when you see them. Now, the other problem we did was problem 53. That problem 53 was a nice problem where we did a lot of basically, we took a real problem and we made up a problem, a mathematical problem similar to the real problem. We had a sphere and inside of it there was a hole, and we said, okay, this, it looks like as if it's a sphere with another sphere inside of it, but the charge distribution is reversed so that we can get a zero charge in there, as if we have a hole. This is similar to when you guys do the center of mass and things like that, and you do actually the same thing. You say, okay, I have a distribution of mass in here. I have the density of the mass in this case is defined by rho. Actually, we use the symbol rho for it too. But in this portion, I have a negative rho, which doesn't make sense for mass. Negative mass doesn't make sense. But for the sake of mathematics, for the sake of calculations, it makes perfect sense. There is no such a thing as a negative mass, but the same method is used there to find the center of mass or to find the moment of inertia, or to do whatever calculations you need. But it's a mathematical method because it's equivalent. As if you took a hole, you made a hole in the actual object of negative mass that cancels the existing mass, so you end up with no mass, you nothing inside, basically. So that's the same method used in that case. Down the road, and I've been saying that several times, we will be dealing with similar problems using that same method, where we'll be dealing with current densities, current flowing in one direction, with a hole in it. There is something that is basically inside that makes it kind of imperfect, not a cylinder or something. So what we do in that case too, in the same fashion, we're going to imagine if the current is flowing one way, there is a portion in it that has the same current density flowing in the opposite direction to cancel the current that is flowing one way, so that we don't really have a current in that place. So again, it's a made up problem. It's really not a real thing. The real thing is still that wire or that basically conduit of electricity with nothing in it. So that is really this method as we're describing. So the purpose of solving stuff like this one in classroom is to get you exposed to different methods of doing problems, so that you guys, when you're actually solving actual problems, it can boil down to one or the other techniques. Obviously, the first method has nothing to do with this problem. Like, for example, the next problem after this one, problem 54, is identical, except the symmetry is a little bit different. Instead of spheres, we have cylinders in there. So that is basically the purpose of this whole thing here. Now, I added to them, like I said, problem 43, and in addition to that, I promised to do problem 55. And you have seen already a good dose of problems similar to problem 55, namely with data, where Excel is invoked. where we're going to plot things and get slopes and things like that to find things. Okay, so this is in a nutshell how this chapter, at least in terms of practice. As I promised, let me first of all put this book away. I'm going to come back right away to it. As promised, let me look into the lecture first, because we kind of left it hanging in the middle of something, and I really don't like the way it ended, honestly, because it ended on some math stuff that has nothing to do with what we're doing, honestly. Just to get you acquainted a little bit with the idea of this partial derivative business, okay? So, normally in physics 4a, basically, in physics 4a, the force derives of a potential and you write it with a minus sign. So somebody asks, why in the world do we have a minus sign in there? And I will tell you why. Because when you are calculating the work of any force, the work of any force is basically in 1D was like this, okay? Force times displacement. So what you ended up with, this must be equal to the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy, KE, not EK. Okay? If the antiderivative exists, so this is between position 1 and position 2. If the antiderivative exists, namely there is a function g, so that if I take its derivative with respect to x, I'm going to get f. That means that this work then will simply be equal to dg be evaluated between 1 and 2, which simply is going to be g evaluated at position 2 minus g evaluated at position 1. And the work energy theorem will tell you that the work, which is just the difference between this antiderivative evaluated at the upper limit and the lower limit, is equal to the change in the kinetic energy. If I do that, what happened? I can move things that have index 2 on one side and things that have index 1 to the other side. So that means this, if I move G2 to the other side, I will have the kinetic energy in position 2 minus G2 is equal to, I'm going to move the index 1 to the other side, I will have the kinetic energy in position 1 minus G1 is equal to 0. Is equal to the same. So that means this difference between these two quantities is the same in the initial and the final position. And for reasons that are completely cosmetic only, aesthetic, okay? People didn't like that minus sign. So this minus sign doesn't look good. It's not symmetrical in a sense. If you switch these two functions, basically kinetic energy and this antiderivative of the force together, you're going to get something where that changes sign. So that is not good. But if it's a positive sign, it's going to be fine because you can switch the order without having to worry about picking up a sign, negative sign here or there. So for that reason, people said, you know what, we're going to call U the potential energy is just minus the antiderivative of that force F. That's why we have that minus sign in here for the force that derives from a potential. So we have it just for cosmetics, for aesthetics, okay? So now in terms of this new U, so we say the kinetic energy in the final time plus the final value of U is the same as the kinetic energy in the initial plus the initial value of U, and this has become known as a potential energy. So the potential energy in relationship to the force is defined as in such a way that the force derives from a potential this way, at least in 1D. You guys remember this discussion that you guys have had in physics 4A? And the reason why there was a minus to begin with, I mean, and the definition for the potential. So this force derives off of a potential U. Case in point, for example, if you're really not too sure about that, the force on spring F is equal to minus Kx, okay? And this I can think of it as minus du over dx. So this is the spring. And when you do that, you're going to find the antiderivative of Kx. Of course, the minus cancels the minus, and that's a good thing, because then U can be just equal to 1/2 of Kx squared plus a constant. If I take the derivative of this one, I will find, if I write, if you wish, if I write f equals to minus du over dx, I'm going to get the same result of minus kx. This is a spring. Did you find this expression, guys? Remember from the spring? The potential energy of a spring? Yeah, that's how basically you arrive to it. Same thing. When you did the potential energy, for example, for the gravitational potential energy, so here is an object on the ground, you take it up, you say, okay, it's under a force minus mg, because I'm taking the y direction this way. So in this case, you say this force minus mg must be equal to some potential, which is gravitational potential energy, minus dy in this case, because I'm taking the y derivative. So you say, oh, then in this case, the function u must be equal to mgy plus a constant, okay? So the difference in potential energy, gravitational potential energy, is going to be mgh, that's all, where h is the height. So this is the potential energy, gravitational potential energy. Does this now sound closer to what you did? Gravitational energy, yes? For the gravity and force of gravity, the weight, mg. And also, okay, at least one person seems to remember these things. Anybody else? Gravitational potential energy, mgh, and the spring energy is 1/2 of m. Okay, very good. A lot of people now remember these things because of that same relationship that I wrote, minus basically du over dx. But again, that's only 1d, okay? In general, though, so this is what I'm going to write, okay? This is where the thing gets a little bit. So in general, what I'm going to write, the force then derived from a potential, if I can write it as of some potential, and the y component is of the same thing minus du with respect to y of the same potential. The force then in this case has the components fx I hat plus fy j hat, okay? If you care to add the z component for this force, it's an fz k hat, where fz, you guessed it, is equal to minus d with respect to z of this potential. So this potential now potentially can depend on x, y, and z in space, okay? So this potential has this form, okay? So symbolically, okay, don't be scared about the next symbol that I'm gonna write, okay? Symbolically, we write, okay, symbolically, and I'm gonna write big caps in here. What happened when you write something big caps? What does it mean when you text somebody everything is in upper caps?
Must be important.
Or screaming at them, okay? Symbolically only, okay? So don't be scared when you see the symbol, okay? We're gonna write the force equals to minus grad. The minus is there, okay? So this is the gradient, and I'm gonna tell you what the gradient look like of this potential u, okay? So in other words, this is basically the business what we have in hand, okay? It's equal to or minus the derivative with respect to x in the x direction, the derivative with respect to y in the y direction, the derivative with respect to z in the z direction of this function u. And that is my force, okay? So this is what I meant with it, that the gradient. So the gradient is a derivative operation, but it's in space, okay? So it's a vector that it takes a scalar, it takes a number like 12. This is a function that is scalar, not a vector, and converts it into a vector by taking its derivative in the I direction and appending it to the x component direction. I'm sorry, there is no minus in here. The definition has no minus in it. The minus is part of just the force in this case, plus the derivative with respect to y, and append to it the j direction, and the derivative with respect to z, and append to it the k hat direction. So this is the definition of a gradient, okay? So that's an extension of the stuff that we have seen earlier. So the force symbolically is written this way as minus grad. Sometimes you write it actually grad minus gradient which is the same thing, of this potential. The point being in here is this is a number. This is a scalar function. And out of a scalar function, you invent a vector function, okay, which is the force in this case. So if a force satisfies this condition, we say it derives from a potential. That means it's conservative. That means its work doesn't depend on the path you take from path to path, from point to point, because friction can depend on the path. For example, let me go to the 1D example, okay? I have a spring, for example, that was stretched this much, and I have a mass in here. And I want to know the work done for the mass going from this full extension down to 0. Okay, down to the equilibrium position. So in this case, I can tell you the work in this case is going to be equal to the change in the potential energy. Here, it has 1/2 of kx naught squared. Here, it has a 0 potential energy because the elongation in this case is 0. So I have 0 minus that. So the work in this case is going to be this number. That's the change, okay? For the force of the spring in this case, okay? Now, you ask, this is the starting point. This is the ending point. How about if the spring goes through this step, not through this one? This is one path. Another path, it can compress completely and come back to it, where the work is still the same. So whether you take path 1 or path 2, which is this complicated path that go back and forth, if it goes many times, if it goes many times, it goes like this. So it left this point, comes in here, goes all the way back to where it started from and comes again. This is the third path, actually. It's still the same work. So it doesn't matter which path you take. However, if I take friction, friction has a problem. Friction, if I just go through path 1, the force of friction is opposing the change in here, this case, and you will dispose of work on this path, okay? That work of the friction is not the same as if you go completely all the way. As a matter of fact, you lose more and more energy if you go here and you come back in here. So the final state will have different work than the first one. So if you just go through path 1 for the force of friction, it's going to do less work, the force of friction, then you have to go all the way back and come back to the same ending point. So although these two paths lead to the start from the same point and end to the same point, but they take different ways of getting to the points. In this case, the work is different for the force of friction. Conservative forces, no, it doesn't matter. For the force of the spring in here, it doesn't matter. The change in the potential in this case is exactly the work, whichever way path you take. Whether you go a million times back and forth and you come back to it, or you go just once, it's the same amount of work. But the friction matters, which path you take. If you go only once, you do less work than if you go twice, which is less work than if you go 3 times before you come back to this one, and so on and so forth. As a matter of fact, you might end up with no energy whatsoever left for you to come back to the starting point. You might not even get back to x naught, let alone to this point in here. By the time you come back in here, you will have less mechanical energy, unless you have a system pumping in energy into your system, in which case, like an engine, for example, in which case the engine will compensate for this energy. The engine itself is actually not a conservative force too, because it adds energy to the system in the same fashion too. So those are 2 examples of non-conservative forces. Either something that is supplying energy to the system or draining energy from the system, those are non-conservative forces. So basically, that is an example. So this case in here, the force is conservative. So what I'm about to show in this case is that the electric field derives of a potential. The electrostatic force, electrostatic force derives from a potential. Namely, F equals to QE derives from a potential, okay? Why I'm saying that? Because if this is just a number, this is just it doesn't depend on R or anything like that, so it does nothing. So if the electrostatic, for me to show that the electrostatic derives of potential, all I have to do is show that the electric field itself derives from a potential. To do that, we will show that the electric field itself derives from a potential. If we do that, we're in business. Then this is a conservative force, and electrostatics is a conservative force, and we're in great shape. So let's see now, can I find a function V in such a way that it's equal to minus grad of V? So I need the function scalar V so that I can write this expression. If I do, then I am in business. So what I'm going to do, I'm going to take a point particle. Point charge, I'm sorry. The electric field for it, I know exactly what it is. It's Q over 4 pi epsilon naught times R hat over R squared. We have seen this several times for a point charge. Then if I am interested in trying to find what I'm saying in here, this expression looks like to me minus a grad of some function V. So if I multiply this by dr and integrate, I'm going to find what this potential looks like. So what this expression look like then is minus Q over 4 pi epsilon naught times R hat divided by R squared times dr is equal to a minus, I get rid of it already, delta V times dr. If I go back to the way that I define business in here, where is it? The grad in this case is a derivative with respect to x of the function V. So I'm looking at this product in here to see exactly what that is. So this is the derivative with respect to x of V. And this is the derivative with respect to y of V. And this is the derivative with respect to z of V times dr. And dr is dx, dy, and dz in general. Okay, it's a component that changes in the x and y direction. So if I do this dot product, component by component, I'm going to end up with dv over dx times dx plus dv with respect to y times dy plus dv with respect to z times dz. This is just the definition of the dot product. The dot product in this case simply just multiply component by component, and that is a dot product. Obviously, this is how the function changes, because delta v with respect to delta x times delta x, this is the change in the x direction, the change in the y direction, and this is the overall change of the function itself, dv. So this is the overall change in v due to all the changes. So if I integrate this expression now side by side, I am finding on the other side dv. So what this thing then says in here is, if I write it carefully, this is just dv. So if I integrate, I have v. That's exactly what the point in here. So v is just the integral of that, and we did it already to begin with. So v is the integral, an indefinite integral of minus q over 4 pi epsilon naught. And again, I just argued the fact that dr, the only thing I'm doing it in the polar coordinates now. I did it, this definition, you can do it in any, the dot product works with any coordinate system. So it's in the Cartesian coordinate system. But in here, since I know the electric field is radial, so it's a useful thing to do actually the integration in polar coordinates, where they are the only thing that is going to stay is just the radial component. The other two components will cancel because of the dot product again in here. So the only thing that is going to survive in the other side is this side. And the integral of minus 1 over r squared is exactly r. And so this is the potential 1 over 4 pi epsilon naught times 1 over r plus a constant. Because don't forget the constants, because we're looking for. So a point charge has a potential. And this is the electric potential for it, for the electric field that it produces. So the electric field is a vector. So if I go back into space in here, so this is charge q, it has everywhere in space an electric field defined in that point. In this point itself, it has a scalar v, where this electric field derives from that potential, where this electric field is equal to minus this definition of v. If it's a one-dimensional problem, I can write E is equal to minus dv, over dx, okay? But it's not a one-dimensional problem. Unfortunately, I have to draw this symbol in here, the gradient. So this is in a nutshell with it, but this is a point charge. And if I'm going to consider more than a single point charge, you guys know who I'm going to invoke. So if I have a distribution of a charge, if I have two charges now, so who do you think we should call?
The superposition principle.
superposition. Thank you very much. I know it's getting old, but superposition. But it's a very important thing in here to how to make the case for all of these things. So by superposition, then in general, the potential is going to be basically the sum of all of this, because each one of them will have a contribution dq and dq. So you're going to sum up through all of these dq's divided by 4 pi epsilon naught times r. And this integration is in space, by the way, plus a constant, okay? It's the constant of integration. So this is basically a continuous sum. If it's just two charges, just do Q1 over the first one and Q2 over the second one in your business. This is the power of the electric potential. The power of it is that once you find that number in space, then you take its derivative and you have found the electric field. So I'm going to leave it at this point in here, because later on when we come, when we do the lecture, next time when we meet, which is going to be on Monday, we're going to take it a step further and start putting stuff now, going back to that dipole and trying to find the electric field for a dipole anywhere in space, not just necessarily as preferred points. We're going to find the relationship between the electric field vector and something we're going to call the equipotential area in there. And that is a powerful stuff, because that will allow us to actually find the electric field geometrically also. And that's what we do in the lab, actually. For finding the electric field, we have 2-point charges, and we take with an ammeter, multimeter, actually we measure the voltage across all of this. And once we measure the voltage, we're going to find the perpendicular to it, and that is going to be the field line. So it's a really fun lab too. One word about the units in here quickly, before we get back into our problems. The unit for the electrical potential is actually a volt. Okay, so it's written as a volt. This is exactly what is in your household: 120 volt, 200 volt, and all of your devices. So it's a volt in honor of Mr. Volta, who did a lot of, actually he invented the battery and things like that. So this is the unit for the potential. So this is the electrical potential. Okay. Once we find the electrical potential, the energy is simple. It's QE, QV. So this is the actual energy. This guy is in joules now, because we removed it from it when we did the integration to find the entire derivative. If we multiply by it, we're going to find the force. And the force basically is, remember, is equal to QE. So there is a one-to-one correspondence between energy in joules and the electrical potential in volt, as much as there is a one-to-one correspondence between the force and the electric field, which is just that Q, which is just a charge, okay? So this basically puts us at stop with the lecture. I know I added half an hour to the lecture, but hoping now to do the problems, okay? Sounds good? Yes, no, maybe? Milo, did you say something? Okay, at least one person, thumbs up. Okay, since problem 55 is all data, I'm going to jump into problem. Can I add a new slide in here, a new page, and call it CH22 problems? Okay, so I know we already did problems 52 and 53, so we're going to do problem 43 now, and then problem 55. Okay, and before actually, I didn't actually take half an hour. I know I talked a lot about the problems first, so not exactly half an hour. Okay, what is my pen? So problem 43. While you're reading the problem, try to draw it and see if it makes, you can pull out any data or information from it, okay? So the problem we're doing is 43 from this 15th edition. And since some of you have the 14th edition, let me look up the 14th edition so that you guys can follow. It's problem 45. 45 from the 14th edition. It's on page 748, whereas on the 15th edition is 744. Okay? It's the same problem. So what they give you in here is a small conducting sphere shell with inner radius A and outer radius B. Let me draw the shape first of all, so that you guys. So we have a shell, I don't know, basically a conducting cell. Oh, a big word in here that they have used, conducting. Remember the previous problems that they were using, insulating? This is a conductor. So this is an important piece of information that you need to pull from the problem. So the inner radius is A, and the outer radius is B. Okay. And then a small conducting spherical shell with inner radius A and outer radius B is concentric, meaning it has the same center, with a larger conducting sphere. Even the other one also is conducting too. And it has also an inner and outer. So this is not a complete sphere, not a solid sphere, if you wish. So it's partially hollow. So it's really, so this portion here is C not A, and this radius in here is D. So this radius is A, and this radius is B, okay? So this is basically the stuff that we're talking about in here. The material of the conductor is in here. So this is conducting. And there is another sphere in here conducting. Okay? So that is an important piece of information here. The inner shell has a total charge of positive 2Q. Has 2Q. Where is the 2Q going to be? It cannot be inside the conductor, so it must be somewhere on the shell, either here, or split between them. Maybe 1Q here and maybe 1Q there. Maybe 3/4 of Q here and the rest is in there, or whatever. So basically maybe half a Q here and 1.5 Q there, as long as they are not inside the conductor. Does this make sense to you guys? Is this understood? That for the fact that is a conductor, I cannot have a charge inside of it. It has to be on the surface. Okay, either on the inner radius or the outer radius. It cannot be inside the conductor. Are we clear on this point? This is very important.
Right. Yeah, Professor, I have a question actually about it.
Yes.
Is this the only important thing we're supposed to pull from the fact that they're conducting shells, or is there something else we need to realize?
This will have an immediate implication. Yes, that's a good question. The fact that they don't have charges inside, the electric field also is inside, so it's 0. So that means that another detail that we're going to pull from this information, no matter whatever they ask us, the electric field in here must be 0 and the electric field in here must be 0. Because if there is an electric field, the electrons are free to move. So they're going to move to cancel it, basically. So that's a good point. So there are two pieces of information that we're going to pull from this statement. Because if this was an insulating and this were conducting, we can only conclude this conclusion about this one. We cannot say much about the other one if it's an insulating. But the fact that both of them are conducting, we immediately know that the charge cannot exist inside the conductor. It may exist on the surface, but that's another problem. Since they put 2Q, I know that 2Q cannot be inside. It can be anywhere, but not inside, okay, of that conductor. That's one thing. The other thing also, and that's a good point, the electric field cannot be any value inside. It has to be exactly 0 inside, okay? The conductor. For both of them, it must be 0 because both of them are conductors. Does this make sense? Yes? Okay. It is very important that you pay attention to the wording of the problems, okay? Now, if it is an insulating, if they're made out of an insulator, then hey, the electric field could be anything inside. And we saw that in the case of spheres where it depends on R and all kinds of nonsense stuff. But since this one are conducting, they're easier in a sense to handle inside. And there is a different story outside, but that's another problem that we can tackle once we face it, okay? So, and the outer shell has actually 4Q charge. Again, I'm going to take a 4Q charge, knowing that this 4Q charge cannot be inside. Okay, this 4Q better be on the shell here or there. Can be on the radius D or on the radius C. It cannot, as a matter of fact, be anywhere inside. Okay, this whole material must have at least a 4Q. I mean 4Q. So I might have 17 Qs in here and negative 13 Qs in there. Same thing in here. I might have 22,302 Qs on one side and negative 23,300 Qs, so that at the end they add up to 2. You guys understand that this is just an algebraic sum. In actual material, I have a huge number of charges. They are of the order of an Avogadro number of charges, but at the end there is a net number of them. Yes? Make sense?
Makes sense.
Okay, so we're in good shape. Now, question A, calculate the electric field E, magnitude and direction. One direction we know is going to be a radial, if it exists at all, because of the radial symmetry, because of the spherical symmetry. So the direction, wherever you're going to draw it, either pointing out or in, and that's the end of it. Okay, that's the only way that makes sense in terms of this spherical symmetry. So the magnitude is the only thing that we're going to worry about it, at least right now, because we know the direction. Okay. In terms of Q and the distance R from the common center of the shells, from the center. So this in terms of R, basically. First of all, I where R is less than A. If R is less than A and we are inside in here, I ask you how many charges are enclosed inside? If I'm going to do a Gaussian surface in here, remember Gaussian surface is a sphere, and the electric field in that section is going to be E times 4 pi R squared is equal to the charge enclosed divided by epsilon naught. Well, how many charges do we have inside?
None.
So the electric field must be 0. So E is 0. So this point in here, anywhere inside the electric field is 0. Okay. So part I, we answered it. It's very easy using Gauss's law without actually having to do a lot of Gauss's law, but we have answered it. Part 2i's. Between A and B. Hey, between A and B, it's a conductor, so it must be 0. R is greater than A, but less than B. E is equal to 0 because it's a conductor. It is a conductor. You cannot have an electric field outside of it. So it's easy to do problems where you have a bunch of zeros, isn't it? And it seems like we're heading toward this one. So at some point, we know the answer is going to be 0 too, because they're taking us in baby steps. From the origin, now we're at this point. Next step, I guess we're going to be here. The third one, we're going to be here. And the fourth one, we're going to be completely outside of this whole thing. Okay? So even if they don't ask it, you're supposed to do it. Okay? So the third question, I. Okay? Where R is more than B, but less than C. Where R somewhere in here. So let me draw it with a green so that we have a Gaussian surface now. We are inside in here. Now we have to do some work, because in that Gaussian surface, again, we're going to use the symmetry. So we are in this case now where R is bigger than B, but less than C. So in this situation, if I use the Gauss's law, again, by symmetry is going to be the same, okay, and pointing radially, because if I rotate it, you're not going to pay attention. So it's going to be radial, and because of symmetry in this case, so it's going to be pointing in this direction this way, and the area is pointing this way, and it's going to be constant throughout the surface, because if you argue one value that is different from another one on the same surface in here, I can rotate this one, and you will have discovered that the thing changed without the actual underlying symmetry changing. Therefore, it must be constant. So at the end this is the one side of Gauss's law. The second side of Gauss's law is the charge enclosed. How much charge is enclosed in this surface, in the green surface? How much charge do we really enclose?
We have 2q.
You guys see that we have a 2q in here? Therefore, the electric field in this side in here is equal to q divided by 2 pi epsilon naught times the distance squared. And it's radial. So if you want to put the hat, you can put the hat on top of this. So that is the electric field. So in here, between this region, there is definitely an electric field, and this is its value. As long as R is greater than B, but less than C. Does this make sense to you guys? Because we really have a charge enclosed now, which is 2q. Okay? So, IV, 4. Okay. What is the electric field between C and D? Oh, we answered that already. Between C and D. That is inside the other conductor, actually. Spherical conductor, spherical shell. And that is a conductor. So what is the electric field in there? E equals to?
0.
Big fat 0. So I'm glad. Look, listen, if this problem is graded, let's say, for example, up to 20 or something like that, you already get a big chunk of the answers already correct just by putting 0, 0, 0. 3 zeros in this problem. The only, probably 2/3 of the problem is already answered. It's very simply because it is a conductor. Okay. Now comes the last part in here. And now you probably have to think, okay? For R greater than D, completely out. So what I'm going to do in here, I'm going to again choose a Gaussian surface of radius R. So think of this one as a big surface that encompasses everything in here. And again, the symmetry argument will say that this electric field must be radial and in the same direction as the area. Therefore, the dot product can become just the product. And it is constant throughout this surface. Therefore, it comes out of the integral, because if you argue that it's not constant, I can rotate these two spheres in such a way that you didn't notice that the spheres have changed. Yet, the value has changed somehow because I moved your value that is not uniform to another value, and we have a problem. So the only way to retain symmetry is that the electric field is radial, and then also it's the same magnitude. So on one side, it's because of symmetry in this problem, it's going to be just E times the area of a sphere, which is 4 pi r squared. On the other side now, it's the charge enclosed divided by epsilon naught. What is the charge enclosed now on this big green surface?
6q.
6q. Do you guys agree that this is actually 4q and a 4q? So there is a total of 6q. Okay. So just by the mere fact that you are completely out does not exclude this 2q in here. So you count all of the q's enclosed, and it's actually 6q. Okay. So this is really the hardest part of this step in here in this problem. So the electric field, and again, I'm going to introduce this one. So it's going to be 3q over 2 pi epsilon naught times r squared r hat. Okay. So that is basically how the electric field depends on r everywhere. Does this make sense to you just by application of Gauss's law and basically the facts that we know about conductors and things like that? Yes?
This probably makes sense.
Okay, very good. So this is part A. Part B of this problem is that it's asking you graph the radial component. Oh, this is part A still. We didn't finish part A. Graph the radial component of the electric field as a function of R. Okay, we're going to graph it, okay? As R. And this is the electric field. I better pick up those points. So this is point A. This is point B. This is the inner shell. This is the outer shell C. This is D. And this is completely out, okay? Inside, the electric field is 0. This region. This region, actually, the electric field also is 0. And inside this one is 0. The second shell also is 0. And outside, it drops like 1 over distance squared. But in here, I have to find the first value in here. So when I plug in the value of r equals to b, it's 0 from one side, and it's not 0 from the other side. It's q over 4 pi epsilon naught divided by b squared. So in here, so it's a discontinuous function, and it starts from this value. And this value is q over 4 pi epsilon naught b squared. And then it drops like 1 over distance squared down to this value. And the reason why it drops to this value this way, and I know this value is less, is because the radius c is bigger, q over 4 pi epsilon naught c squared. Because c is bigger, this number is less than the other one because you're dividing by a smaller number. So it's going to drop there. And then it's going to be a discontinuous function. It says 0. And then at the end, it's going to come up when r is greater than d to be just this quantity in here. I need to pick it up at d. And at d, it's going to be a value that is less than this 2 because of the fact that 1 over d squared again is less than 1 over c squared because d is bigger than c. So q over 4 pi epsilon naught d squared, that is when it starts from, and it starts going like this. So this is a discontinuous function, and that's how it behaves. Does it make sense to you guys? This graphing thing? So it jumps from 0 to something, then it drops, then it goes down to 0. Then it starts with a less because of the fact that we are far away now, and it goes to 0 and reaches 0 at the end because at infinity it's going to be 0. So that's part A. Part B now. Where is my drawing pen? Part B now. Okay. What is the total charge on the inner shell, inner surface of the small shell? If I look at the electric field in here, anywhere, the electric field is 0. Okay? And the electric field, if I apply Gauss's law to it, so where's part I, okay? For the inner radius, or the inner shell, that's what they call it, for the small sphere. Namely, r is equal to, what is it, a? For that, because if I look at this one in here, the electric field in here is 0 inside the conductor. Since it's 0, 0 times 4 pi r squared. Again, I'm just applying Gauss's law in here. This must be equal to the charge enclosed divided by epsilon naught. What number for the charge enclosed need to be to make this relationship correct? What is Q then on this shell?
0.
Has to be 0. So there is a 0 charge in here. So the 2Q must be on the outer shell, okay? You guys see that? So the 2Q must better be here because there is nothing on this one. Because if I take any Gaussian surface inside in here, it's going to have a 0 electric field times 4 pi r squared is equal to the charge enclosed divided by epsilon naught. The charge enclosed divided by epsilon naught, therefore the charge enclosed must be 0 in order for this equation to work, okay? So on the inner shell is 0, just by going back to Gauss's law. Part 2, it's probably guess the outer surface of the small shell. So basically when r is equal to b, what's the charge there? Again, I'm going to take Gauss's law here. And Gauss's law, we already used it to find the 2Q. Again, by conservation of charge, it must be 2Q. It cannot be inside. It cannot be r equals to a. It must be r equals to b. So there is a 2Q charge now. 2Q charge on the inner, on the outer, on r equals to b. Okay? Does this make sense to you guys? Without really having to do a lot of arguments. We can use a conservation of charges, as a matter of fact. But you can use Gauss's law too to make the case for it. Make sense? Yes? Okay. Probably 3 is going to be for R equals to C. Let's check. For R equals to the outer surface of the small shell, that's we did already too. Part 3, inner surface of the large shell. That means, yeah, R is equal to C, exactly. Well, again, if I do a Gauss's law in here, we have 0. Okay, so here is a problem. So we're going to take that surface in here. So we have 0 charge on the inner. We have 2q in here, sitting in here. And we have this third surface and the electric field in here. So there is an outer surface that I'm not drawing in here. So this is the conductor. There is a 2q outside in here. And in here, E is equal to 0. So if I apply Gauss's law on the surface, I have 0 times 4 pi r squared must be equal to the charge enclosed divided by epsilon naught. The charge enclosed, I already know that I have a 2q on this side. So how much do I need in here to cancel this 2q? How much do I need to put in here? Oops, what is this? How much do I need in here to cancel this 2q so that I end up with 0 in here?
Negative 2q.
So we need negative 2q so that we end up with 0. So there is a negative 2q in here. So that this law still applies, that the electric field is 0 inside the conductor. For it to say 0 is equal to 0, I really need to the charge enclosed in this Gaussian surface. Okay, which encompasses both the inner shell completely and this radius of the outer shell. So I must sprinkle the 6q that, no, the 4q that I have in here somehow. Negative 2 of q must be here. Okay, so there must be at least a 6q in here, okay, outside, to compensate for, to add up so that it's 4q altogether. You guys understand? I know they did not ask that, but probably they're going to ask for R equals to D, the outside. And if they ask, we know the answer. It must be 6q, because 6q minus 2q is exactly the number of charge on this conductor. Does this make sense for you guys why it has to be negative 2q first? Because it's coming from this application of Gauss's law for this big sphere that is inside the outer shell, and that encompasses the inner shell altogether, which has 2q, we know that, but also encompasses the inner radius, if you wish, the inner surface of the outer shell. So the inner surface of the outer shell must have a negative 2q to compensate for the other 2q, so that the Gauss's law still says 0 equal to 0, because there is no electric field in here. E is equal to 0. That's why I put 0 in here times 4 pi r squared. So this must be true. Do you guys understand now that the charge q, the charge is negative 2q on this surface of radius C? Make sense? Everybody? Okay, yeah, good. That's just by application of Gauss's law. Now, the outer surface altogether, how much it's going to be, I just argued for it. So it's probably IV. IV. The outer surface, so that means R is equal to D. And for that, I just argued by conservation of charge. If I have 4q altogether, and I have negative 2q in the inner one, therefore the q on the D must be equal to, the charge on D must be equal to positive 6q, okay? So the charge on the conductor will adjust itself to make things happen. So why did the negative 2 migrate in here? No, negative 2q migrate in here? Because it needed an electric field to be 0 inside. And it saw that there is an electric field in here, or there is charges in here. So it needed to compensate for them. So negative 2q will come in here naturally. So if there was 0 charge in this outer shell, negative 2q must come in here to compensate for this one, and the outer shell will have actually a positive 2q in that case. so that there is no charge in here, okay? So that is natural stuff in here, just because of this charge in here. So it induces a -2 in such a way that there is no electric field inside. Otherwise, if there is no charge in here that's going to sit in here, you'll have actually an electric field in here, and that's a problem. Since there is an electric field, charges will move, electrons actually will move to make up for that difference so that there will be no electric field. Once that's established, you're fine. Does this problem make sense to you guys?
Yeah, it makes mostly sense to me. But could you go back real quick and just revisit the charge at R equals B for a moment?
Okay, let me go back into sharing the screen. Share. Okay, for R equals to B, where is it? This one, okay? Here is the deal. We know, let me use a different color. We know if I take a Gaussian surface, first of all, in here, why didn't it change? Gaussian surface in here, there is no electric field. Therefore, there is no charge inside. So there is a zero charge in here, period, end of the story. Because you cannot have a charge anywhere. First of all, inside is empty. There is nothing in it, so we don't worry about it. It's this shell in here that we're worried about it, because, I mean, it's that surface that we're worried, because we said that electric charges on a conductor, they can only reside on the surface. There cannot be any charge in there, because if it does, then there is an electric field in here that goes to, E times 4 pi R squared is equal to the charge enclosed divided by epsilon naught. But because there is no electric field inside the conductor, there must be no charge inside. I know the overall conductor has 2q charge, okay? And there is nothing on the inner surface and there is nothing in the volume. So where would it go? So here, I just argued that it cannot be there. And in here, there is 0 because it's a conductor, but I know it definitely has a 2q charge. That's the problem. They tell you that that conductor, the inner shell, has a 2q charge. So where would you put it? You cannot put it inside, you cannot put it on the inner surface. So where is the room for it, Milo?
Oh, so we just make the assumption that R equals B has the full charge because R equals A is 0?
For R equals to A, the charge must be 0 because of Gauss's law. For R equals to A, the Gauss's law says in this case, the electric field, which is 0 in here inside the conductor, because it's a conductor, it has no electric field, times 4 pi R squared is equal to the charge enclosed divided by epsilon naught. Which charge would you put on the inner, on R equals to A, to make this relationship true? How much would you need to put to make this 0, because there is no electric field in here? How much would you need to put? It has to be 0. So this A cannot have a charge in it. If it does, we have a problem in here, because you cannot have 0 equal to something, okay? So that's why we have 0 in there. Now, we know the conductor overall, the inner shell conducting shell, has a charge 2q. That charge 2q is forbidden from being in the middle. Why? Because it's a conductor, okay? Inside the bulk of the conductor, it cannot exist. It has to be on the surface. The inner surface cannot exist on it because of the fact that we just argued, because it does not satisfy Gauss's law. So where would you put it now? It's not an assumption. You have no choice in the matter. Do you see that, Milo? Why you really have no choice in the matter?
Yeah, I got it. I got it now.
It has to be on R equals to B. It cannot be anywhere else. Okay? That's a good question. Is everybody is good with this question? Because we have another problem at least. Good. We have another problem that we need to discuss too. Let me share with you guys the screen and tackle problem 55. No, I know it's an hour already. So, and things like this one gets tiring after a while. I know that. And the retention starts to go down the hill after that. And actually my focus myself goes also completely out of the window. So we really need to expedite this problem too. I'm not going to do Excel because oh man, am I sharing with you the screen or?
No.
I didn't share anything. Sorry, here is the screen, okay? Because I thought I was. Okay, so problem 55. And I don't know what problem it is right now. If you guys are doing 14th edition. Okay, let me quickly glance at the book in there.
don't see problem 55 on the 14th edition. Well, if you don't have it, there is problem 59 that is similar to it. Okay?
But you need to understand how these problems are tackled, okay?
It's problem 50 in one experiment, the electric field is measured 4 points distance r from uniform charge that has charge per unit length lambda.
Actually, it's problem 59. I'm sorry, it's problem 59, okay? On that book. Okay. So it is problem 59. So problem 55. Problem 55, basically, in one experiment, the electric field is measured for a point at a distance r from a uniform line distribution. So you have a line distribution in here. At a distance r from it, in lecture we use the symbol y. It doesn't matter. Don't be stuck with the symbols. You can use whatever symbol you like. Okay. From a uniform line of a charge that has a charge per unit length lambda. So we know that this has charge per unit lambda, and where L is the length of this wire is much longer, much bigger than r, so that we can assume that this is an infinite rod. So basically, in that case, we know the electric field in this case, if you guys remember from lecture, is lambda divided by 2 pi epsilon naught times the distance r. Okay, this we saw it in lecture. Okay. In a second experiment, the uniformly charged insulating sphere that has volume charge density rho. So in another one, what we did, we took a rho charge distribution in this case, and so it has rho charge, and it has a radius r that is equal to 8 millimeter. So it's a small sphere, okay? So this distance is 8 millimeter. And then where r is bigger than r. So we're measuring at a distance r from it, okay? So we know the electric field in this case behaves like as if it's that of a point particle, except that the charge instead is just the entire charge of the sphere, basically divided by r. It's an insulating. That's why I'm using this expression. If it's not insulating, it's still, the expression is going to be correct as long as you're outside. If it's a conducting, inside the electric field is going to be 0, so that all of the charge is actually on the shell, on the outer, basically, surface, okay? The results of the two measurements are listed in the table. So basically, you have a table that gives you r. The r is in centimeter, okay? And gives you measurement A for the electric field, E, and E is in 10 to the power 5 Newton per Coulomb. You have to know that number, that this is the conversion rate. So it gives you a bunch of data for the x-axis and a bunch of, the x-axis, yes, for R. It gives you 1 centimeter, 1.5 centimeter, 2 centimeter, 2.5 centimeter, 3 centimeter, 3.5 centimeter, and 4 centimeters, so in increments of half a centimeter, okay? The electric field is seen to change, of course. Both of them will diminish as distance. Both of them are decreasing as we move away. So the first one starts from 2.72 all the way down to 0.677, basically decreasing with the distance, okay? The second one starts from 5.45 and decreases all the way to 0.335, okay? So both of them are dropping like one over distance. If you move away from this one, the electric field is less and less. If you move away from the sphere, the electric field is less and less. Both of them are, but they don't tell you measurement A and measurement B. For each of this set of data, draw two graphs, one for ER squared and versus R, and one for ER versus R. So basically, you're supposed to take all of that data, put it in an Excel spreadsheet, and basically draw this 4 graphs. You're going to have 4 graphs at the end of the day. So let me see if I can quickly do these things in Excel. Where is my Excel sheet? In here, and share with you. And hopefully you see me struggle through this. Excel. I assume that you guys will be comfortable by the end of this stuff and here doing stuff on Excel on your own. So let me stop sharing that screen and share with you my Excel spreadsheet in here. So here is what we're drawing in here. We have, first of all, R. It's going to be in centimeter, okay? So it's important to remind yourself what this is. So R is in centimeter. and it's 1. Actually, you can use what the okay, it's just few data here. I don't have to do an autofill in here. 2, 2.5, 3, 3.5, and 4 centimeters. Okay, so these are the data in here. And then the electric field for experiment A. So E sub A, and this is in powers of 10 to the power 5. Okay, Newton per Coulomb. So it's an SI. So it's 2.72, 1.79, and then 1.34, and 1.07. And what else do we need? 0.902, and 0.77, and 0.677. Okay. And then same thing in here, except that this is B, not A. So experiment B, the data are 5.45, 5.45, and then 2.42, and then 1.34, and then 0.861, and then 0.605, and then 0.443, and finally 0.335. Okay, so this is basically the data that we have. As you can see, the electric field actually has 3 sig figs, whereas there are 2. These are fixed values. These are known. Okay. So what they want us to do is take this value and multiply it by R and draw the graph. Take this value and multiply it by R squared and plot the graph. So we're going to take the first one in here. So it's experiment A, EA. So the first set of data is going to be equal to the electric field times this number, and copy this stuff, okay? It's going to be in the units of 100,000 times 10 to the power. So probably we should convert things, okay? Okay. So we probably should, oops, escape. So we probably should do that. But you know, this is in a Newton per Coulomb times 10 to the power 5 times centimeter, okay? So we're going to do the same thing now, is equal to, again, I probably could define the units and do things like that, but for right now, that's going to be fine. So E times this one squared. Okay, so it's not going to change because it's 1, but this numbers probably will change, okay? So I'm going to say this is 1 for being linear, and this is EA2 for being quadratic, okay? So we're going to take this thing in here, and we're going to plot it with this one and insert. Actually, can we do 2 plots at the same time? Insert graph in this case. And as you can clearly see, one of them is a line, is a fixed line, and the other one is a linear function, okay? One of them corresponds to, if I multiply it by, so which one is the blue? The blue is this one. So this is R times E. If I go back to the theory, let me go back to the theory, stop this one, and share with you the theory. In the theory, what happened in here? Did I delete things? Okay, it's still here. So if I multiply E times R in here, this should be constant, just lambda over 2 epsilon naught. Whereas if I multiply this one, I'm sorry, if I multiply it by R squared, it's going to be linear in R. It's going to grow linearly with R. So this is actually the rod, because it gave me a constant value for EA1. Let me go back into the Excel spreadsheet and do the other two, okay? Where is the, let me stop sharing that screen and share with you the Excel spreadsheet. Move this a little bit out of the way here. And now do EA2, okay? EB1, oops, 1. And then we're going to do EB2. EB2. Why is it? No, I lost the. Okay. So this one is going to be this cell times this one. And this one is going to be equal to this cell times this one squared. So that's basically the two values. So I'm going to copy those two cells and paste the formula in here for the rest of them. So this is the data for the second experiment. So again, I'm going to draw this one as my x-axis and this one as my y-axis, insert, and it's going to be this plot again. Okay. Oops, why is the chart title in here? Okay, so if I multiply it by this, the blue one is still this line. So if I multiply it by r, let me go back into the expression here. Let me stop sharing and share with you the theory to see exactly what's going on in here. If I multiply this one by r, it still drops like 1 over r. It goes basically like a what do you call it? A hyperbolic function. Or so it basically goes to 0 when r goes to infinity. But it doesn't really, it's not linear, really a line. But if I multiply it by r squared, it just becomes a constant, q over 4 pi epsilon naught. So from this graphs, let me stop sharing this theory and share with you the Excel file. Obviously, EB2 indicates that this is actually the sphere because it drops like 1 over distance squared. Because if I multiply these numbers by this number squared, I get straight line. Whereas this one, if I multiply it by just this number by r, I get a straight line. I get a linear approach because it grows linearly. And this, because I didn't multiply it by enough powers, when I multiply it just by r, because it still drops like 1 over distance. Okay. Do this. Excel's graphs make sense to you guys, depending on the theory. Yes? Okay, very good. Then at the end, the results, okay, of the two experiments are shown. So we'll draw 4 graphs. That's what they ask us to draw. They draw E times R for both experiments and E times R squared for both experiments. And from there, you're going to tell which one is which one is actually a sphere and which one is actually a rod, okay? Use the graphs in part A to calculate lambda for the uniform line of charge and rho for the uniformly charged sphere. Okay, let me go back into the data and see exactly how we're going to do that. Share with you the Excel file. This line in here tells me, if I'm careful enough with it, it tells me the value in here that is constant, okay? So this is the value that is constant. Since this is the value, I can find its average if you like, okay? If I want to, equals to average of this side in here. So that is the constant I'm looking for, okay? And if you want to do statistics, you can find the standard deviation, you can find the error, you can find the R squared, you can do all kinds of things in here to see with how confidence this is actually a line, okay? And whether or not this average is very close from the actual value or not. And that will be lambda over 2 epsilon naught, 2 pi epsilon naught. Since you know the value of epsilon naught, and you can convert, you have to convert things. You have to make sure you're working in SI. Make sure this one is in centimeter and then plug back the 10 to the power 5. And now you have a value for lambda, which is going to be in coulombs per meter. Does this make sense to you guys on how to find lambda from this data? Okay. Now we're going to look at this data again. This is the one that is closer to constant, okay? So this is, again, this number and this number. So all of this. So again, we're going to do the same thing equal to, actually, we can copy this expression and go anywhere. Oh, man. That's not good. Okay, so we'll have to do it. I thought we were going to, because I didn't define a range. If I defined a range, then we will, in Excel. Hopefully you guys are mastering Excel by now. So again, we're going to do the same thing in here. This is the average, 5.4. Now this looks like it's not straight line, okay? So there may be more errors in this one. So there is probably more errors in this experiment in here. This one, this constant, again, make sure that they have a proper units. You have a 10 to the power 5 in here, and this is centimeter. Don't forget it's squared now when you multiply it. They didn't multiply it like the first case by just a centimeter. So there is a 10 to the negative 2 in here, squared, which is 10 to the negative 4 in this case. So if you do the calculation and you're careful enough with it, you're going to go back. Let me go back into the this one in here. You're going to, because you multiplied by r squared, to find this constant now, which is just a constant, which is the average of all of those constants, q over 4 pi epsilon naught. Now we can find q. Once you have q, you can just divide it by the volume of the sphere, and the volume of the sphere is just 4 pi r squared. Not this r, it's this r. So rho will simply be just the q that you calculated from the other one divided by 4 pi r cubed, where r, not r squared. Did I say r squared for the volume? That's stupid, I'm sorry. It's this volume, this radius in here for the sphere. Now you have rho, and you answered the question. Does these two problems make sense to you guys? In addition to the previous two problems that we did in this case?
Yeah, that makes sense. I think I just need to practice with like Excel and data for sure more.
Okay, very good. So you guys know what to expect. So I'm hoping that you guys practice a lot of these things. I know some of you are not here today. I'm going to make these recordings available for you today. And the assignment, whenever we do problems, is you check my numbers because I make mistakes, okay? Check them. Make sure, first of all, I do approximations. It's rarely that I do calculators. So do that. And then check the rationale. Maybe I made a mistake somewhere in the solution or something. So please let me know and understand everything that we're doing to learn the methods on how to do these things. Sounds like it's a good plan?
Do we have any discussion questions from this lecture?
From today, yes, in the morning.
But not the lab session.
No, not the
Okay.
lab session. The lab session is still the same thing, which is whenever we do problems, and this is true all the time, you are supposed to basically go through them yourself and then plug in the numbers and let me know if I did something wrong or something not clear or something like that, okay? Good, Milo?
Yeah, I'm good.
Okay. Okay, I'm gonna end it now. The reason why I'm doing that is because, first of all, I know the lab time is extended thing and it's already an hour and 25, and we really did an hour and 25 not too long ago, about less than half an hour ago or something. So it's too much time, things to take. So I'm giving you, and myself actually, rest a little bit so that we can go through other things, and hopefully we see one another. Next week we do lecture, and maybe the lab also will be available for you guys, because we would have introduced the capacitance at that. Sounds good?
Yeah,
Good.
I think
Thanks,
sounds
Professor.
good.
We'll see you on
Okay.
Monday.
Okay, see you Monday, guys. Take care, okay? Don't
Yes.
forget your homework assignments, okay? I'm gonna stop the recording now.
Thank you.